Wonderful. So again, I'm thanking you very much for the very kind invitation to give a seminar talk today about my ongoing project studying black holes and black hole binaries in quadratic gravity. The talk will be based on a series of papers, in fact. So the first series of papers was in collaboration with Hector Carrera Silva, who's a postdoc at the Albert Einstein Institute in Germany, one of my PhD students in London, Matt Alley, and one of my colleagues here at the University of Illinois, Nico Yunus, and another series of papers led by Banafsheh Shiralilou, who is a PhD student at the University of Amsterdam, who has done really impressive work, and I will point that out as we go along in the talk. Tanya Hinderer, Samaya Nisanka, and Nestor Ortiz. And as you may guess from the title of the talk, The Adventures of Black Holes, I actually shamelessly borrowed that from my favorite Sherlock Holmes novel. So I really enjoy reading those crime mystery stories. And one quote actually has stayed with me in particular. So let me take the time to read that to you. So this particular quote is from The Adventures of the Bruce Partington Plants, and Sherlock Holmes and his sidekick James Watson are, discussing one of his of Sherlock's theories, and Watson says, "Oh, this seems most improbable." And Sherlock responds and says, "Well, we must fall back upon the old axiom that when all other contingencies fail, whatever remains, however improbable, must be the truth." And in some sense, we are playing detectives, gravity detectives, using black holes and gravitational waves to understand new phenomena in physics and fundamental physics. And in some sense, we are still at the place where we are trying to gather evidence to understand observational signatures and phenomena before we can even, distinguish between impossible or improbable and incorrect. So what the talk today will be about is how we can gather evidence, how we can provide theoretical insight into what observational signatures should be if we have compact binaries, in this case, black hole binaries, and how they may impact our observables. And the observable I will be focusing on are gravitational waves. But that's only one part. So let me actually ask a much bigger question. We want to play gravity detectives. There are quite a number of questions in fundamental physics that are still unanswered. So one big question is, in cosmology, and the question is, what is dark energy? What drives the late-time acceleration of our universe? The other question is, related to a dark matter and particle physics. And actually, one of my research programs involves studying a certain class of dark matter candidates using black holes. I'm not going to talk about this today, but you're welcome to ask about it after the regular talk. Where the talk today fits in is this red box up here, where the big over-encompassing question is, what is quantum gravity? How can we consistently combine gravity and quantum physics? But if we know that Einstein's theory of general relativity is not a good candidate for quantum gravity. I'm not going to pretend that I'm coming up with new models. I have very capable colleagues who have done that. But my question is, if we have these candidate theories for quantum gravity, what would be this, the observable signature that would allow us to either find them or constrain them or even rule them out to a certain degree? And that's what the talk will be about. For all of these big questions, we typically look at extensions either of our standard model of particle physics, for example, if we look at dark matter candidates, or we look at extensions to general relativity that are motivated, in the case that I will be looking at, from these quantum gravity paradigms. And with the new observations of black holes and gravitational waves, we can now test general relativity, or more generally test gravity, in the strong field nonlinear regime. Okay, now we also now actually have the data to do so. So the first image that I'm showing you here is the image of a shadow of a black hole taken by the Event Horizon telescope, where we see the shadow of around the black hole at the center of the galaxy M87. The other really impressive amount of data was found by our ground-based gravitational wave detectors, first by LIGO, later joined by the Virgo detector in Italy, and since just before the pandemic, also the Kagra detector in Japan. And this is the latest image from the LIGO-Virgo Kagra collaboration, showing the black hole and neutron stars observed in gravitational waves since the first detection in 2015. And what we see here on the left is the mass of our compact objects in units of solar masses. We see here a couple of neutron star plus neutron star collisions ending up either in a very massive neutron star or very light black holes. There's still question marks on that. And here in blue, we see this impressive number of well over 50 black hole collisions that we have now detected. That is to say that now we are really entering an era where we have data of black hole collisions. So we are actually entering a phase where we can start doing precision gravitational physics and use those observations to understand both astrophysical processes, but also to address some of those questions in fundamental physics that I mentioned in the very beginning. And I also said, well, if you want to compare data to theoretical predictions, do we actually have good theories? Do we actually have good predictions of what we can do? And well, yes and no. So one thing that the LIGO-Virgo-Kagra collaboration has already done is to be relatively agnostic about the specific model that we want to look at. So if you take your black hole, and you model the, or really compact binary, if you model the very early inspiral phase, when the gravitational field is weak, velocities are still relatively slow, you can use an approximation that is called a post-Newtonian approximation. And what people have done was to take these post-Newtonian approximations and which is an expansion in velocity, a characteristic velocity of our binary over the speed of light. And these different orders, post-Newtonian orders, essentially correspond to different orders of this velocity over speed of light. And now what people are doing is to take each of these coefficients in this series expansion and modify that. So add a free parameter to that coefficient. And what you're seeing here in the plot, unfortunately, probably not as clear as I would like that to have been, is constraints from observations. This one is actually from earlier this year, where the black hole, so the gravitational wave observations were used to constrain some of these deviation parameters. And you see they all basically seem to indicate that the modifications are close to zero. But there are also a couple of caveats to that. So first of all of this essentially assumes general relativity as a null hypothesis. So not one deviation from general relativity was taken as a null hypothesis here. So it's actually very much focused on that one. Also, at the moment, only one of these parameters is varied at a time, whereas your different theories may actually have to vary two parameters at a time. So the question is, how consistent is this kind of variation, and how informative is this? And it also only focuses mostly on the inspiral part. So it doesn't take into account and doesn't even probe for deviations in the merger part, basically because we are still lacking specific modeling of black hole mergers in extension of the general relativity with very few exceptions. So there has been quite a lot of progress in the last few years, but we are not even close to the situation where we are in general relativity, where we have inspiral merger and ring down on a day-to-day basis and with the precision and accuracy that we would need. And the next question, of course, is even if we can have these constraints, can we consistently match these theory agnostic tests, which are very efficient, to a specific series of gravity? And also, in this case, to do that, we do have to have at least a few examples of really gravitational waveforms in extensions of general relativity. So what I want to do for the rest of the talk is actually focus on one of them. Because although we do have, we can ask, do we have series to test? And the answer is yes, we have plenty. So you can ask, 5 different colleagues working in the field of modified gravity, and they probably give you 20 different answers. But the other question is, do we have concrete observable predictions? So what I would like to do today is take one example or a class of examples really, and show you how we can obtain these observable predictions, and also how that helped us to find a new nonlinear effect that I will come to in the end of the talk. But maybe I should pause here for a moment just to check if there are any questions before I continue. Okay, so I don't see any. Then let me just go ahead and actually tell you what I will be talking about today. So I will focus on a specific concrete class of theories that's known as a scalar Gauss-Bonnet gravity. I'll show you the action on the next slide, but think of this as a theory that contains curvature squared type terms in our action. So these curvature squared kind of corrections, or higher curvature corrections in general, may become relevant in the strong curvature regime of gravity. Some versions thereof can be derived from or are inspired from the low energy limit of string theory, and there were actually a bunch of papers in the late 80s, early 90s showing that. And for me, I'm usually taking a little bit more agnostic approach here. This theory or class of theory that I will be talking about today is actually a representative for a much wider theory class that contains quadratic curvature terms. So we will be able to see kind of the main effects, the main phenomena in this kind of series. Okay, so what does it look like? Well, the action is here. So we have our standard Einstein-Hilbert term here in the first term. We are coupling the gravity to a scalar field. So here's a kinetic term of my scalar field, phi. And then we have a non-minimal coupling here between the scalar field and this curly G is a Gauss-Bonnet invariant. So that's the Riemann tensor squared minus the Ricci tensor squared, so minus 4 times the Ricci tensor squared plus the Ricci scalar squared. So a couple of comments before I continue. So this coupling constant here, this alpha GB, is something that is dimensionful. This has a dimension of mass squared. So later on, I may actually use a dimensionless version thereof to present my results. I would also like to point out that if we didn't have this coupling with a scalar field here, so if this f of phi would be 0, then in for space-time dimension, the Gauss-Bonnet invariant would just be a total derivative and would not contribute to your field equations. So we do get modifications in the field equations because of this coupling to a scalar field. And this function of the scalar field, f of phi, actually selects different subclasses of this theory. So for the sake of this talk, I distinguish between 2 types. So let me talk about the first type first, and then I will go to the second type. So what I labeled type 1, scalar Gauss-Bonnet gravity, are those models where the derivative of this coupling function with respect to the scalar field never vanishes. So examples for that is if the coupling function just goes like the scalar field itself, or if you have a dilaton type coupling, so if the coupling function goes like the exponential of our scalar field. In those cases, we can show that the scalar field equation is always sourced by something that doesn't vanish times the Gauss-Bonnet invariant. So it's always sourced by the space-time curvature itself. And we always have non-trivial scalar configuration. So we get hairy black holes. So with a scalar hair. The second type of scalar Gauss-Bonnet gravity series are those for which the derivative of the coupling function with respect to the scalar field can be zero for some values of the scalar field. And the examples that will be important here are a coupling function that goes like phi squared, or people have also looked at a version that goes like the exponential of phi squared. In this case, we will end up with effectively a Klein-Gordon equation with an effective mass term. And if the scalar field is zero, then both the Kerr solution of general relativity and the Schwarzschild solution of general relativity are still solutions in this theory. Whereas if the scalar field, the scalar field can be spontaneously excited and actually form bounds around the black holes, given a certain value for the coupling constant. So we can have spontaneous scalarization, spontaneous excitation of the scalar field. So what I will do is to first talk about signatures of this first type, and then I will go over the second type here. Good. So let's look at type 1 series, where the coupling function, as I said, or the derivative of the coupling function with respect to the scalar field will always be non-zero. We've already seen the example. So if the function goes like the scalar field itself, typically leads to series that are shift symmetric, so that we have an extra symmetry here, or where we have this dilaton kind of coupling. For the results that I'm showing you, I will mostly focus on this case where we have shift symmetry. But a lot of the arguments go through similarly for the second version here. Now, what does the scalar field equation look like? Here we have the box operator acting on our scalar field. In general, on the right-hand side, here we have the coupling constant, the derivative of the coupling function, and that's why I made such a fuss about it, and then times the Gauss-Bonnet invariant. And if this term never vanishes, we always have the Gauss-Bonnet invariant here as a source, which will be a non-zero and actually will source the scalar field. So we always have scalar hair, scalar hair of the second kind, if you're familiar with that terminology, for the black holes. Yeah, so our black holes will now be described by the mass and spin. And they will have a scalar configuration where the scalar charge is also determined by the mass and spin. Okay, and in one of the first studies where I looked at this scalar Gauss-Bonnet gravity series, we actually showed that the scalar hair can form dynamically. So we've done basically as a first code test, and to understand how this scalar hair forms, we just started with a single black hole. We worked in the limit where we are not back reacting the scalar field onto our spacetime. So we basically have in the background just a single spinning or non-spinning black hole, and evolve the scalar field on top of that as sourced by our background. And we have seen that even if we start with a zero scalar field initially, it will always be sourced by the curvature. And at late times, we saw that the scalar field would approach the solution that you get by solving this equation, for example, in spherical symmetry. Yes, so we have shown numerically that the scalar here actually forms dynamically. Good. So the next step was to now take two of these black holes and let them inspiral for about 10 orbits and merge. And what we will be looking at now is the evolution of the scalar field sourced by this background. So I will again work in the decoupling limit, where I'm not including the back reaction of the scalar field onto the space-time. I will be interested or show you the dynamics of the scalar field here. To do that, I have implemented the the equations for Gauss-Bonnet gravity in my library Canuda, and Canuda is actually fully compatible with the open source Einstein toolkit. And Canuda is also available, it's also open source in this Git repository indicated here. By now, we actually have a few collaborators who contribute to different parts of that code. So in addition to being able to simulate this black holes in scalar Gauss-Bonnet gravity, we also have a collection of code modules that allow us to study massive scalar fields or massive vector fields. So if you are interested in any of those, you're welcome to contact me or have a look at the repository. Good. So what we will be looking at now, using this implementation, using this infrastructure, is actually work that I've done a few years ago with Leonardo Gualtieri, Paolo Pani, and Thomas Sotirio, where we evolved in the background two black holes, one with a mass ratio of 1 to 2. So one, had a mass twice as much as the other one. And as I said, they orbited for about 10 orbits and then merged. So let's look at the scalar field here. And what we'll be seeing is the equatorial plane of our scalar field. So let me make that a little bit bigger. Yeah, so we have the equatorial plane here. The color is encoding the amplitude of the scalar field. And we see here, these two bulges are centered around each of the black hole. The larger scalar field bulge is actually centered around the smaller mass black hole, which has a higher curvature. And as we see those two black holes orbiting around each other, they have each of them a scalar monopole charge around each of them. And as we are already familiar with from, for example, electrodynamics, if you have two monopole charges orbiting around each other, they create a dipole charge. So that's what we are seeing here as well. The excitation of scalar dipole charge that's emitted from the system. And now we actually have the merge of the black holes in the background. All non-axisymmetric modes of the scalar field are shed away, and we are left with a final axisymmetric solution of the scalar field. Good. So let me stop the animation here, because now we can also ask, well, what does it actually do to our binary system if we have the scalar dipole radiation that can emit energy, that can dissipate energy from the system? If we have this energy dissipation, we would expect that our so if we had back reaction, right? So now, in this case, we don't, but if we now assume that the scalar field would be back reacting onto our spacetime, what would happen is, because we're dissipating additional energy, our binaries would black holes would actually inspiral faster. If they inspiral faster, that should lead to a phase shift in the gravitational wave signal. And we've done this calculation explicitly in the regime, in the post-Newtonian regime, where our black holes are very far apart, gravitational fields are still relatively weak, and velocities are slow. Now, people have looked at this from about 10 years ago, led by Ken Yagi, Nico Yunis, Takahiro Tanaka, and Leo Stein, who computed the energy fluxes using this kind of post-Newtonian approach, assuming that our Gauss-Bonnet coupling, the dimension is Gauss-Bonnet coupling, so that's why we have this division by mass squared here, is very small. Felix Gillier and Emmanuel Aliberti have also looked at the sensitivities and the two-body-Lagrangian for these kind of theories. But that still didn't give us explicitly the gravitational waveform. So that's the work that we have done together with Banafsheh, Shirali Liu, Tanya Hindra, Samaya Nisanka, and Nestor Ortiz. And here you see an example plot of that work. I know it's a very busy plot, so let's focus on this middle panel and the bottom panel here. So what are we seeing? In the middle panel, we have this strain H plus as a function of time. And in the bottom panel, we see the evolution of the frequency as a function of time. For the sake of having a specific example, we looked at a black hole binary with a mass ratio of 1 to 2. And we set the initial point such that when our black hole binary enters the LIGO sensitivity band at about 10 Hertz, our black holes in either Einstein's gravity or this modified, so the Einstein-Dirac Gauss-Bonnet gravity are aligned. Okay, and now what we are seeing here in black, the black curve here and here corresponds to the black hole, the evolution of the black hole binary in general relativity, and the blue curve corresponds to the evolution of our black hole binary in this scalar Gauss-Bonnet gravity, where we have a coupling function that's e to the phi. And what we see very clearly here is that initially our waveforms are basically aligned, and you can also see that here in the inset on the left-hand side. But as the evolution continues, and as we have this additional scalar dipole radiation, dissipating energy away from the system, our black holes start inspiraling faster and faster. And you see here after 60 seconds, we are, which is here indicated in yellow, or here in the middle panel, we already have quite a bit of dephasing. And here at the end, close to merger, which is indicated by the red lines here, we are really completely dephased and have a much larger amplitude here. And this is the gravitational wave signal. Yeah, so this is basically the signal that LIGO could detect. So this is something that we could already use for doing data analysis. Yeah, so what's still missing here is actually having the merger, including the back reaction of the space-time. So here we are only very close to merger. So to get the full inspiral merger and ring down signal, we would now have to stitch this to numerical relativity waveforms, and that's work in progress. Okay, so that's all I wanted to talk about for this type 1 theory. So again, let me pause for a moment if you have any questions in between before I continue. Okay, so if not, then let me go to this second part, type 2. What was type 2? Let me just remind you. So in this case, we have a coupling function. Oh, and this shouldn't be a phi 0, this should just be a phi. The coupling function would be of the form phi squared, or something like e to the phi squared. That is the derivative of this function with respect to the scalar field would go like phi times some constant, or phi times some exponential. Now, if we insert that in the scalar field equation, we get this form here. I've written this in a slightly different form now. So again, we have our wave operator here acting on the scalar field. I've introduced a different coupling constant here just to distinguish that from the type 1. And again, we have here the derivative of the coupling function times the Gauss-Bonnet invariant. Because of the structure of this coupling function, we now actually can write our scalar field equation as a Klein-Gordon equation with an effective space-dependent mass term for the scalar field. Now, what I'm showing you here on the right is actually the phase space of solutions in this theory. It's actually the phase space for nonlinear solutions, where we show the coupling constant measured in solar masses squared as a function of solar masses. Good. And what turns out is that in these kind of theories, the solutions of general relativity actually still exist. So if I look at this phase diagram, everything that's here in white corresponds to the phases in this phase space where we still have Schwarzschild or Kerr as the solution. And in fact, it was shown that if this effective mass term, which goes like minus second derivative of this coupling function with respect to the scalar field times the Gauss-Bonnet invariant. So if that effective mass term squared is larger than 0, any perturbations would decay, and the Kerr solution is actually the unique solution. However, if we, for whatever reason, this effective mass term here becomes negative, then that gives rise to a tachyonic instability. And that leads to a spontaneous scalarization of black holes. And what you see here in this phase space, in this gray, blue, and red line are in fact these scalarized black hole solutions. So for specific values of the coupling function or coupling function versus mass, we can have black holes with scalar hair. But outside those regions, our standard hairless bald black holes are still solutions. Now, the other interesting fact is that if you have rotating black holes, then the Gauss-Bonnet invariant can be negative in some regions of the space-time outside the black hole horizon. And in this case, you can actually also find spin-induced scalarization if this coupling function, second derivative thereof, is negative. And as we go along, we will see examples of both of those. Okay. So when we started our first project on this, which was published earlier this year, we actually started off and said, okay, wait a second. So if we can have the spontaneous scalarization of black holes, what would happen if we put it in a binary system? Well, we are not the first people looking at scalarization. In fact, another completely different system, neutron stars in scalar-tensor series, are also known to be spontaneously scalarized. So let's have a quick interludium and look at what happens there. So in Browns-Dicker type scalar-tensor series, you can write the equation for the scalar field as a wave operator acting on the scalar field, which is proportional to some constant times the scalar field times, and T here is a trace of the energy momentum tensor of your matter. And in this case, you can also find a tachyonic instability. So isolated neutron stars can spontaneously scalarize, and that was realized by D'Amour and Esposito Farese back in the early 90s. Now, if you join me now in early 2010s, different groups like led by Shibata and collaborators, or Carlos Polenzela, Enrico Barauza, Steve Liebling, Louis Lehner, collaborators, have looked at binary system of such neutron stars. And what they found is that if I have two neutron stars who are not scalarized, who are just our, plain, really interesting neutron stars, if the binary becomes compact enough, then they actually can dynamically scalarize very close to the merger. And the other setup that people have found was that if I have one neutron star that's scalarized, the other one that's not scalarized, they orbit around each other, the binary becomes more and more compact, and they found that the second non-scalarized star can become scalarized through induction. So that's the story for neutron stars and scalar-tensor series. And when we first started off looking at black holes in this Gauss-Bonnet gravity series, we thought, oh, maybe we can, so if we can have single black holes spontaneously scalarized, maybe we can find dynamical scalarization in binaries. So that's what we thought basically at the end of last year. And we performed the first study where we focused on the simplest setting that you can imagine, two black holes. We're not even orbiting yet. So that's ongoing work, but we just looked at head-on collisions. Yeah, so make the system as simple as possible. Let's collide the black holes head-on and study the evolution of the scalar field as sourced by this background. And we looked at 4 different scenarios. Again, we've implemented that in our library Canuda here, and we've looked at 4 different scenarios. So the first one was to start with 2 black holes that were not scalarized. So this S bar means they are not scalarized, and that's kind of where we were hoping to find scalarization. And to our big disappointment, turns out the scalar field never grew. Nothing was happening. It was the most boring simulation ever. Then we looked at a case where we had one of the black holes scalarized. So this is indicated by this S, and the other one is not scalarized. And let me actually show you in an animation what's happening in this case. So here, as I said, we have, again, the scalar field evolution in the equatorial plane. So the white lines here indicate iso-curvature contours of the Gauss-Bonnet invariant, and this will hopefully run on a loop. So we have the larger mass black hole here. This black hole here has half the mass of the other one. And we have the black hole, the smaller mass black hole here on the right being scalarized. And now as they collide, of course, they form a final larger mass black hole. And to our surprise, the scalar field dissipated, as you can see here. Now, why is this happening? Well, the reason for this, what we now called dynamical de-scalarization, is that our final black hole has a larger mass, meaning it has a smaller curvature. So if you just look at the Gauss-Bonnet invariant or the Kretschmann scalar on the horizon of a black hole, it goes like 1 over the mass to the 4th. So what's happening is as our black holes collide, forming a larger mass black hole with a smaller curvature, the curvature is no longer sufficient to support the scalar field, and the scalar field will just dissipate. Okay. And a similar effect we find in many cases where we start with two black holes that are scalarized, both of them scalarized in the beginning. And if the coupling constant is, not too large, we again find this dynamical de-scalarization. And only if we really crank up the coupling constant such that we are sure that the final black hole must be scalarized, like in this green case here, then indeed the final black hole will be scalarized. And to see that a little bit more clearly, I'm also showing here the scalar field monopole mode, rescaled by the ray. So I'm basically evolving my system. I have a sphere of fixed radii around the system where I measure my signal. Yeah, that's what I call the extraction radius, and this is what this Rx is here. So I'm showing the scalar field monopole times this extraction radius, so the radius of my extraction sphere, as a function of time in my evolution. I'm measuring the evolution time in terms of the total mass of my system, and I've shifted the scalar field waveform such that t equals 0 in my coordinates corresponds to the time of merger. And as you can see, so the black line here was a case where we didn't have any scalarization in the beginning, and the scalar field was never much excited. So we did put a small perturbation on this, but it just dissipated, and this is what you can see here. The red curve is what we saw in the animation, and red and blue are both cases where one or both of the initial black holes were scalarized. We can see that before the merger, indeed, we have the scalar charge, the scalar field present, and after the merger here, we see that it's basically just decaying. And only in the case where we really cranked up our coupling constant did we, so before the merger, that led to an exponential growth of the scalar field because we are still working in this decoupling limit. And after the merger, the scalar field settled down to a roughly bound state configuration. Okay, just one more comment. So if you're interested in looking at the different, well, not this one because it's boring, but the other cases, we have them on the website that's associated to this paper and also on our YouTube channel. So if you're interested, I welcome you to go there. And I would also like to mention that more recently there has been work by Will East and Justin Ripley where they came up with a formulation of the theory that allowed them to include the back reaction of the scalar field, but only for small couplings. So they've also started looking at similar kinds of system. What we are doing instead, and that's work in progress, and that will be my last slide on this topic, is to now actually look at the evolution of the scalar field if we have a black hole, an inspiraling black hole binary in the background. Now, why is this still interesting? because we can now have different effects. Remember, I was making this comment about the Gauss-Bonnet invariant can be negative in regions of the space-time if our black hole is spinning. Well, if I have an inspiraling black hole binary, then if we have, at least if their masses are equal, then we will reach a black hole, a final black hole that is rotating fast enough so that we may have the spin-induced scalarization. So with one of my students in London, we actually looked at both cases. So we have looked at one case where our black holes initially were spinning with a spin of 0.6, so dimensional spin of 0.6, and aligned with the orbital angular momentum. And initially, we just gave a very small scalar field perturbation onto the system. So let's look at this evolution first, and this is actually here on the left. So in this case, after our initial data has settled a little bit, we now have here our two black holes, both of them rotating. And with a scalar field perturbation in the system, we see that now these two black holes become scalarized. And as they orbit around each other, they finally merge, give us a burst of scalar radiation. But then now with the larger mass black hole, actually the curvature of the spacetime is no longer strong enough to support our scalar field. And again, we have dynamical de-scalarization after the merger. And this last bit you can ignore. I'm sorry, I should have stopped. So this is just noise from the boundary that's coming in here, and which looks particularly strong because the scalar field is shown in the amplitude of the scalar field is shown in a logarithmic plot. Yeah, so the message to take away from here is that, first of all, because we had these initially spinning black holes, we actually saw the spin-induced scalarization in both of the black holes as they orbited around each other. And after the merger, after the mass increased, curvature decreased, the scalar field just dissipated. Okay. The other case that we looked at, and sorry, here I should actually not have a bar on this end. So here we looked at the case of two black holes, equal mass, orbiting around each other, having no scalar field initially, and we were hoping to find spin-induced scalarization during the merger, because the final black hole will be rotating with a spin of roughly 0.7. In this case. Well, let's have a look at this. So here again, we have our two black holes. What we are looking at is the evolution of the scalar field in the equatorial plane, so the XY plane here. Again, the color encodes the amplitude of the scalar field, and we are looking at a logarithmic scale here. And as you can see, the black holes themselves, they weren't scalarized initially. And it seems like the maximally boring evolution here. So nothing is happening to the scalar field all the way, not even during the merger. And now only well after the merger, like we're now about 200 M after the merger, we see the scalar field growing from this spin-induced scalarization of the final rotating black hole. So in some sense, we have here an example where the modifications to general relativity, this extra scalar field, has been hidden throughout the entire inspiral, even during the merger, and only well after the merger, where basically the final black hole will already have been wrung down to a single rotating black hole, do we see the growth of the scalar field through this tachyonic instability. Okay, so this part, I should say, is still in preparation. So we are currently writing up the paper with these results. Now let me come back to my initial statements and questions that I had, where I said, can we actually identify observational signatures in these series, and can we use that to place constraints on some of these extensions of general relativity? So let me just remind you of the first cases that we looked at, this type 1. And here we always had black holes that carried a scalar here. Yeah, so this was this first animation that I had shown you, where the black holes had scalar here, orbited around each other, and produced scalar dipole radiation. Also in this case, the final black hole is always scalarized. Yeah, this additional scalar radiation is leading to a dephasing of the gravitational wave signal, and the final black hole is this hairy black hole that can possibly modify the ring down. And actually, the study of this dephasing of gravitational waves, or the absence thereof, has been used to place observational bounds on this coupling parameter for the Gauss-Bonnet coupling if you have a shift symmetric or a diatonic type of coupling function. And the most recent paper is by Scott Perkins and collaborators, who is also one of our students here. Okay, so far so good. What's the story about the second type that I talked about, where we have this spontaneously scalarized black holes? Well, we've seen that situations where our black holes may have been scalarized initially, but leading to a non-scalarized final state. But if I just focus on the inspiral of these two scalarized black holes, I would expect that the presence of the scalar field again would give rise to scalar dipole radiation, which dissipates energy from the system and would lead to a dephasing of a gravitational wave signal. The other interesting case is the one that we saw in the very end, where we had two non-scalarized black holes that led to a solution before the evolution before the merger that is identical to the evolution in general relativity. And in contrast to what we were expecting, the scalarization didn't happen during the merger, but only well after the merger. Yeah, so in some sense, here our modified gravity effects seem to have remained hidden for most of the evolution, so may not even give an observational signature within our gravitational wave signal. Good. So with that, I will just summarize what I told you today. So I was focusing on the phenomena and potentially observable effects that you would get in black hole binaries if in our theory of gravity we have a coupling to higher curvature correction. I focused on scalar Gauss-Bonnet gravity. Many of these effects are somewhat similar if you look at a theory that's known as dynamical Chern-Simons, where you basically have the parity violating counterpart to the Gauss-Bonnet invariant. I've also shown you that at least in a large number of cases, we will have scalar radiation before the merger that eventually leads to a phase shift in the gravitational wave. And after the merger, depending on what subclass of this class of theories we are looking at, we can either have a hairy black hole or dynamically de-scalarized bald black hole. And we've seen some examples where beyond GR effects actually remain hidden and may never show up. Now, there are several follow-up questions directly related to this program, which is to include the nonlinear evolution. That means the back reaction of the scalar field onto the space-time. And here again, one may ask, how does it impact the gravitational wave radiation? Can we actually now compute that explicitly? What would be the merger? What would be the end state? It would also be interesting to extend that to other quadratic gravity theories, such as this dynamical Chern-Simons theory. There have been works for single black holes already by people like Daniela De Neve and collaborators. And actually, with my new postdoc and one of my new students, we are looking at that for the binary case now as well. And of course, eventually, once we have the theoretical predictions, when we have the theoretical waveforms, we would want to really place observational constraints from binaries or single black holes on these theories. So with that, I thank you for your attention, and I will take questions now.
Thank you, Helvi. So any questions? Okay, Francis put a question. he's asking, how does the scalar field affect the formation of black hole itself?
Okay, so that's actually a really, really interesting question. And that's something that we are finishing up now with one of the students here, where we study just the collapse of a single neutron star into a black hole. Now, the story here is the following. If you have a neutron star, then the scalar field to leading order at least vanishes. So the scalar field charge, the 1/r part of the scalar field is 0, and only higher order terms like the 1/r to the squared enters. So you can think of this neutron star actually as not having a scalar charge, right? So, and as a neutron star collapses, you can start forming the scalar field. Yeah, so only once you have your curvature singularity do you form the scalar here. Does it answer your question?
So, any other questions? Maybe I'll ask a question. So, as you mentioned that both type 1 Gauss-Bonnet, type Gauss-Bonnet, they both introduce dephasing. So this means dephasing compared to the regular binary black holes.
Exactly, exactly.
But yeah, so, but LIGO needs to do, or any other gravitational wave detector needs to do reverse engineering. So how is that possible that when we are detecting, when we are doing reverse engineering, how is it, yeah, how well can we reconstruct those modified gravity or other, yeah.
Yeah, so that's a study that's actually still, at least in my point of view, missing, right? Because what LIGO does at the moment is these parametrized studies. And the constraints that I quoted on the previous slide actually uses that parameter. So you take your inspiral waveform, you add these parameters to each order in this post-Newtonian expansion, and then you try to constrain these parameters, right? And what people, so the constraint that I mentioned on the previous slides actually uses that constraint on the parametrization and translates that into a constraint on the coupling function. But what we haven't done is actually take inspiral merger ring down waveform in extensions of general relativity, because they're still really scarce. So I've shown you one example where we have just the inspiral, but still not the merger, right? But I think doing the study of, can we actually recover a signal that's beyond GR, and can we identify whether it's a non-GR signal, or would we interpret that as GR just with different parameters? This is still outstanding. And I think this is a really interesting study that needs to be done.
Okay, yeah. Yeah, I think in order to do that, you might need a maybe faster way to create a lot of templates.
Yeah, but I think, so yes and no. So I think at this moment, I would be happier if you had even proof of principles studies of whether or not we can recover beyond GR effects. But I think that, yes, this is still kind of missing. So we are still at the stage of actually computing the inspiral merger and ring down waveform in specific series beyond GR. Right. So yes, long term, definitely, you're absolutely right.
Maybe can I ask another question? Back to the slide you show the head-on collision of type 1 to head-on.
So I think that was the second one, yeah.
Yeah, can you go back to that slide?
Of course. Yeah, let's just go here. I know this was, sorry, this was a very busy one.
That one. In the diagram D, that's two scalarized black hole that generates another scalarized black hole after merger. So and what you plot is the monopole of the scalar field, scalar head of the black hole. So it's introduced so it has goes up in the inspiral or ring down phase. Do you know why is that?
I do. So remember I said we are looking at the decoupling limit. So we are not actually back reacting our scalar field onto the metric, which means all we can actually recover or find is the onset of this tachyonic instability. Yeah, and everything above this the critical coupling for the tachyonic instability, we will have scalarized. If we were to include back reaction, then actually let me go back one slide here. So you see here the solutions that we have, so nonlinear solutions that we have. Yeah, so if we have only the decoupling limit, we would find only the onset. So we would only find here the right line, and everything above this line would be gray because that would all give rise to a scalar field. If you include nonlinear, if you include back reaction effects, then you see that your solutions actually only have this band structure. So if you increase your coupling parameter too much, you again will not have a scalarized solution. So so what's happening here, oops, sorry, let me just go back to this slide. Because we are only working in the decoupling limit, we only see the onset of this instability. So we always have the scalar field present, and because we have to increase, so in this case, we increase the coupling constant so much that the final black hole would be scalarized. But that also led to large growth rate of the scalar field. And that's why we are going up here to very large values. So to do a proper study, we would actually have to include back reaction effects here. Yeah, and that's why I think it would be very interesting to study that. Yeah.
Thank you.
Mm-hmm.
So,
yeah, I could ask a couple questions too, but I think we're going to talk in a little bit. So,
so yeah, we can ask more questions if you are. Yeah, you're welcome to stay. Thank you, Helvi, again for wonderful talk. And thank you, everybody.
Okay, thank you. Yeah.
I also wonder what's the